last time we were talking about mutational analysis, and we talked about how we can, just by trying to understand what's happening to the free energies of the folded and unfolded states, determine qualitatively what a mutation is going to do. Okay, so this is really essentially asking do you know qualitatively what's going on structurally in both states when you make those mutations? And the reason you have to consider both states is because the stability is the free energy difference between those two states. So considering just one state is not adequate. Okay, and I think the best example of that is this first example we started last time, which is taking a residue that's on the surface and turning it into an alanine, a hydrophobic residue on the surface, and turning it into an alanine. We do our little thought process where we say, okay, what happens to the free energy of the unfolded state? What happens to the free energy of the folded state? And we talked about the unfolded state going from leucine to alanine. First thing we ask ourselves is, what's the environment around the residue in the unfolded state? And so tell me, what's the environment around all residues in the unfolded state? Water. It's covered by water. Okay? Water is the environment. So it's an aqueous environment. And all the residues, to a first approximation, are experiencing the same sort of environment. So leucine in one position is more or less like a leucine in another position. It's not the same as alanine, obviously. Okay, so if we're going from leucine to alanine, how do you think the free energy of the unfolded states interaction is going to change? Are we going to have a more favorable situation or a less favorable situation having an alanine in place of a leucine in water? Don't think about the folded state, because that doesn't matter here. We're only talking about the unfolded state. More favorable, right? Less nonpolar surface, less hydrophobic effect, lower free energy. That's how you should think about it. Okay, so indeed that's what happens. So that unfolded state, free energy goes down in the mutant, okay, because there's less nonpolar surface exposed to water. Now, in the folded state, okay, what would be going on? What's the environment of this residue in the folded state? It's on the surface. Okay, it's also in water. It's also touching water. It's its primary interaction. Is that a bit of an oversimplification? Yes. But it turns out it works. Because, in fact, you would also expect the free energy to go down because there's less nonpolar surface exposed to water. And so what we have here is we have a mutation that's clearly changing the interaction of the environment, but the interaction is the same, okay, change is the same to a first approximation in both states. And this corroborates the mutational study I showed you before, where Kai Zhang went through all the amino acids and alpha helix, changed each one to alanine one at a time, and the surface substitutions basically had no effect, okay, on stability. That's true, by the way. The majority of the surface residues, if you substitute them, will have no effect on stability. They might have effects on solubility. That's not what we're talking about here. We're just talking about stability. Okay, so stabilities are similar, okay, and like I said, the main key element is that if the residue doesn't change environments when the protein folds, no matter what you do to it, it really is not going to affect stability. Okay? Because you'll have both states moving the same amount up or down. Okay. Now let's go to what's a bit more interesting. Now we have a large buried hydrophobic residue in the core of the protein. And before we get moving, let's think about what's the environment around that residue in the folded protein. We already know what it's like in the unfolded protein. It's covered with water, and that's always the answer there. Okay, but in the folded protein, what's the environment like around a buried leucine, typically? Okay, it's surrounded by generally nonpolar residues. What else? When you say surrounded, what are they doing? Okay. They're interacting by how? Don't say hydrophobic interaction. Van der Waals. Okay, they're interacting by Van der Waals. So they're closely packed. I mean, that's an important point. They're not floating in a vacuum. Okay, they're not shielded. They are shielded from water, but they're closely packed with other residues. They're tightly fit, and they're not moving much. Okay, so there's a lot of things going on there, which is typical for an interior residue. Now, go back to our diagram. What happens to the unfolded state free energy? Well, this is no different than the previous situation, because again, everybody's exposed to water. So really, changes in unfolded state free energies are generic in the sense that they're the same approximately for all residues. What about in the folded state, though? What's going to happen here? How's that residue going to affect the free energy of the unfolded state, and why? Okay, so first of all, visualize what's going to be you have a leucine. Now you're taking it out. What's there going to be? How's the protein going to deal with it? Yeah. Yeah, you're going to lose van der Waals. So that makes the free energy less favorable. So that's going to go up. What else? What else? I just made a big residue and I made it small. Yeah, I'm going to make a hole in the protein. Somebody said cavity. Okay, I'm going to make a hole inside the protein. Okay, so what are the ramifications of that hole? Well, one of them, of course, is that you lose van der Waals interactions. You don't have them anymore. But the other thing is you're creating unfilled space. And somebody mentioned water. It turns out if it's a nonpolar environment, water will not go into there for any length of time. Actually, it's free access, can get in and out, as it turns out. But it will not stay there because there's no hydrogen bonds there. Okay? And so you now have an increase in free energy of the folded state due not only to the loss of van der Waals, but also to the creation of unfilled space. That is an entropic penalty. Okay? To make unfilled space in anything is going to cost you energy. All right? Preventing the universe from filling up everything is going to be costly. So the net result now is that I've had a downward shift of my unfolded state and an upward shift of the free energy of my folded state. That has pushed these two states together. This is going to be destabilized. This free energy difference is a lot less than this. Okay? How big? Well, it depends. But in general, for leucine-alanine substitutions, you get anywhere from 2 to 5 kcals per mole, roughly, destabilization in a model like T4 lysozyme. And what I'm going to tell you is that it is always unfavorable, okay, to substitute a large buried hydrophobic residue for a smaller one because, one, you have less stabilization of less hydrophobic stabilization. And what I really mean by that is that the free energy of the unfolded state goes down. That means you're already pushing the folded and unfolded state free energies closer together. Even if nothing happened to the folded state free energy, that would still be destabilizing because you're not getting that energy by burying that large residue anymore because it's not there. That turns out to have entropic effects from the hydrophobic effect and enthalpic effects from the hydrophobic effect. And what these are is going to depend on temperature. This is always going to be a reduction in free energy of the unfolded state. This one will really depend on what temperature you're at. That component, if you're talking about temperatures below 20 degrees, making an alanine will actually be enthalpically unfavorable. It will actually raise the free energy of the unfolded state because the classic water molecules are combined more strongly. But if you're above 20 degrees, it would be the opposite. All right. So that's the first thing. The second thing is that you're losing van der Waals contacts. The third is that you have this cavity penalty. Okay? So all of these changes are unfavorable for the folding process. They reduce the free energy of the unfolded state and they increase the free energy of the folded state. Okay, structurally going on, what happens? So this is a kind of view. Can you guys see okay? Okay. So this is a blown-up view of T4 lysozyme, and there's a bunch of things shown here that I'm going to explain to you. It looks like a lot of spaghetti now, but if you kind of look at it, you can see what look like alpha helices, I hope. Okay? These are helical segments. These are just showing the alpha backbone, carbon backbone trace. There's just a line connecting the alpha carbon atoms. And we're looking into a helical bundle, so these guys are coming out at you. Okay? And I've taken away almost all the side chains except for the ones that do something interesting in this mutant. So forget this netting, just look at the side chains now. So I hope you can see through the morass there that there's a red leucine, okay, at this position. And it's been changed to an alanine. The backbone of the wild-type protein is shown in red, and the backbone of the mutant protein is shown in green. Okay? So the first thing that happens is obviously make some unfilled space. Okay? If the protein did not change its positioning, in other words, if nothing moved, okay, in the protein, then we'd have a cavity as large as this big purple thing. That's the inside of the cavity, but I just took the model of the protein, of the wild-type protein, took the side chain out and calculated the cavity. It would be this giant hole through the entire protein. Okay? That's not what happens because the protein attempts to shrink that cavity. And it does it really in three major ways. One is that this phenylalanine, which is nicely positioned down here in a very favorable conformation, now actually becomes mobile. It actually moves up, trying to fill this hole, and it also is wiggling a lot. You can see that in the electron density. It has a funny-looking shape, kind of spoon-shaped electron density. Another thing that happens is this leucine that's right next to that cavity also rotates into it. And what's significant about this is it actually rotates into a conformation that is really not favorable. Okay, it's a strained conformation. And the question is, there's nothing pushing it to become strained. So why is it doing that? Well, it's doing it in the attempt to fill space. So in other words, you're incurring unfavorable local changes to try and reduce the amount of space taken. And that's a lesson, is that all this is a big trade-off. You have local changes and you have global changes. The global change is what's determining the energy, but the local changes can be unfavorable or favorable, but they have to be compensated in some way. So the net result is the cavity that you end up with after all the... Oh, the third thing that happens is that, I hope you can see, this is a little bit more subtle, that the green lines generally are inside the red lines. That means the whole protein has collapsed a little bit. In some cases very subtly, where you can very see it right here. But here, this is a really big rotation. It's about a 1.5 angstrom shift of that helical end alpha carbon, basically rolling into the cavity to try and fill space with residues that I'm not showing here. Okay? So the proteins are plastic. They do not stay rigid when you do things to them. And in this case, you can see clear expressions that unfilled space is unfavorable because the protein is trying to shrink it. Okay? And so you have a cavity that shrinks by 74 cubic angstrom, but it still leaves behind a very substantial size cavity. And then that happens by side chains and overall collapse of the structure. So this is typically what happens when you try and make holes in the middle of proteins. They do things like this. An example of a protein that doesn't move really at all when you try and fill in, make a hole, is this mutant leucine 99 to alanine. So shown here is the alanine substitution at position 99. The leucine will fill this space here, which I'll get back to what's in there right now. But instead, you get a cavity that is basically like this red netting. And it turns out that the protein almost doesn't move at all, okay, when you make this substitution. Why doesn't it move? Well, obviously, it can't. The costs of movements are too high. So for this particular residue, there's nothing that can fill in the space, so it just basically sits there. However, it clearly wants to have its space filled because if you take these proteins and soak them in benzene, okay, or expose them to benzene vapor, then very quickly benzene finds its way into that cavity. You can see it crystallographically, and this is the structure actually of the benzene bound in the cavity. So benzene is nonpolar. It wants a nonpolar environment to go into, and this environment wants to be filled. Filling space is entropically favorable. It also gives you favorable van der Waals interactions because this is actually a rather disc-shaped cavity. Why leucine 99 isn't a phenylalanine is because this wouldn't really, if there's a phenylalanine here, it wouldn't be able to fill the cavity in the same way that this benzene does. It just happens to be kind of disc-shaped. Okay. And then, of course, the hydrophobic effect drives the benzene in there. Now, one of the curious things is how does benzene get into this cavity in the crystal when there's no path to the surface? That's another lesson here. That in fact, protein structures, even in crystals, are fluctuating enough to open up at least a couple of angstroms to let this in. So every once in a while it goes like this, or like this. In solution, that is on the microsecond time scale, because that's the rate limiting step for the benzene to get in. You can measure that using NMR and look at the dynamics of the benzene, and it takes microseconds to enter the cavity. Okay, so that's really pretty fast for our time scale. For other time scales, that's not fast. Yeah?
Why does taking out leucine make such a big point?
Well, because that's the environment around it. I don't mean to give you a fresh answer. It's just different parts of the proteins have different density of packing. This turns out, I didn't tell you this, but there is actually a naturally occurring cavity in T4 lysozyme, which I'll show you actually on one of my later slides, that this one just makes bigger. So right adjacent to this is actually a naturally unfilled part of it. Okay, good question. Okay, yes, sir?
Do we see a difference in flavor? Has experience been done with leucine going to like valine or something of that sort? Like, is there a similar result, like just a lot less scale?
Yeah, the problem when you make leucine to valine is that the amino acid, and we'll talk about that, has a rather different shape. Okay, and so you start having additional costs on top of creating cavity. So this is a nice clean experiment. You're taking something out, you're not changing it to anything different. And so, so that allows actually a generalization in this particular case to occur. And again, does anyone else have any questions? Again, I'm going to have to go to my thing here. So in the end, it turns out that I think I'll just best show this to you as data before showing you the slide. What happens when you clean out here? So hopefully no one will be too horrified. I'm going to use the back of your Maxi project. It will still get scored, don't you worry. But I forgot to bring, Sometimes I feel like just kind of battling the world here. All right. Oh, that's right. It's this thing. There we go. Yay. All right. Okay, ignore the writing on the back there. So what was done is to ask the question, so if you make a bunch of leucine alanine changes in the same protein, you compare them, you find that you get a pretty wide range of destabilizations, anywhere from 2 to 5 kcal. Okay, for the same substitution. So that's telling you that, not every leucine is doing the same thing or having the same situation. And so what was noted was that actually the remaining space left over, after you make the substitution to determine the structure, is different in different cases. Why is that? There are different densities of packing in different parts of the protein. There are different sort of incipient cavities that get opened up. And so if you just simply graph the change in free energy of folding, stability change, versus the volume or surface area of a cavity, you get a relationship that looks something like this. Okay? It's roughly linear. So that's telling us that the difference in substitution, or difference in destabilization from different substitutions has to do with how much unfilled space is left over. That's what it's telling us. And you can actually get a slope for this number, which is about, depending on how you calculate it, 20 to 30 calories per angstrom cubed surface area. Volume change. So basically assessing the size of the cavity. And then the intercept here is actually rather interesting. This is what the destabilization would be if there was no cavity left over. In other words, if the protein was able to completely collapse the cavity. This is what you lose. And it turns out that's about 1.8 kcals per mole. And what's significant about that is about the solvent transfer free energy difference between leucine and alanine. In other words, that's the energy that we don't get for varying leucine. Instead, we get for varying alanine. That difference is about 1.8 kcals per mole. And when you think about that, no matter how small you shrink the cavity, you still are not going to get that energy when you fold the protein. So actually, it's a very satisfying result in the sense that now we have a number here which actually agrees very well, oddly enough, with calculations that have nothing to do with protein structures but have to do with the cost of creating unfilled space in solvents in order to dissolve ligands. There's a whole thing called scale particle theory that deals with this. Don't ask me much about it because I don't know much about it. But the answer that comes out is that creating vacuum costs about that much. Now, this is a curious result because, of course, that also has folded into it Van der Waals contacts as well as cavity volume. It has to sort of make up for both, but this is the number you get. And I'm just going to leave it there. So this is approximately equal to the delta G of transfer for leucine minus alanine. All right. Okay, so that's pretty interesting. So we go back to here. And now, so there's this linear relationship between cavity size and stability. And so, in other words, you can predict, if you knew everything, what the change in free energy would be by first looking at what happens to the unfolded state. This is really the energy by which the unfolded state drives. It pushes the two states that much closer together in energy. And then what's going on in the folded state, is this so-called cavity term, which has both the entropic cost of forming a cavity as well as the Van der Waals interactions, that you're losing when you take away that size. Yeah.
So the delta G transfer would be in the leucine alanine case, that would be 1.8.
Yeah, that's right. So this is your intercept term, and this is your cavity volume dependent term. So this allows you, to guesstimate the change in stability. You can certainly guesstimate what the maximum change in stability is going to be. And as I said, in the leucine 99 to alanine case, where there's no movement, it basically falls right on the line, but where there's movement otherwise. Now, as I said, some proteins are able to almost completely shrink the cavities to zero, but not quite. So that's why there were some dots that were close to the y-axis. Okay. The other thing that you learn from this is that getting rid of big residues doesn't gain you anything. Because you might imagine that maybe, you're stuffing too many things into a place there's some strain involved, and sort of putting them all together and taking them out might release that strain. Pretty much what this tells us, if there are terms like that they're very small, okay, that there really is no inherent strain inside of a normal folded structure. And that actually also makes sense because evolution has had plenty of time to rearrange things so that there isn't a strain. Were you about to raise your hand? Okay, it's fine. Okay? Okay. Speaking of strain, all right, so let's talk about kind of the opposite type of substitution than what I just talked about. Does everyone understand making cavities is always destabilizing, no matter how you do it? Whether you convert leucine alanine, valine alanine, isoleucine alanine, it always destabilizes. There has been a study of valine alanine, and roughly speaking, it gave the same result. Okay? Isoleucine alanine is a little tough, there wasn't enough isoleucine to really cover the whole protein. So now we're going to take a small residue and we're going to make it big. Okay, that's here. And we're going to just do this with hydrophobics because we don't want to talk about other more complicated things. We just want to talk about really packing, okay, and van der Waals interactions. So again, we're on the surface of the protein. We have an alanine, we're going to a leucine. So you guys do this one. So what's going to happen to the free energy in the unfolded state when I go from alanine to leucine? Free energy going to go up or go down? Which is more favorable, having an alanine or a leucine? Alanine. So the free energy is going to go up because it's less favorable. So right away, okay, you have a higher free energy unfolded state. The protein folds up, okay, this is a surface residue. What's going to happen to the free energy of the folded state? It's also going to go up. You have to, one of the things you guys got to remember, okay, you really have to think of each state in isolation and what its free energy changes are. Don't think about the other state. Okay, now that you know both go up, it turns out they both go up about the same amount because, again, the environments are similar, and so you get no net change. And again, just to reinforce this, okay, that essentially surface substitutions, and this be clear, involving polarity or size changes. Other types of substitutions could do things, and we'll talk about this, but polarity or size changes are generally neutral, okay, because there really isn't a different environment between those two things. Okay. So if you feel like you've heard that enough, good. However, when we get inside the protein, things become more interesting. Okay, now we're talking about an alanine going to a leucine inside the protein. What's the environment around that alanine like? In the folded protein? What's the environment around that alanine like? It's tightly packed. Most interior residues are tightly packed. Doesn't matter how big they are. Okay? Alanines aren't next to cavities generally any more than any other residue. Okay, so we have a tightly packed situation, and now we're sticking a lot of extra stuff in there. So what's going to happen? So first of all, we already talked about the unfolded state free energy. It's going to go up, right? Because there's more nonpolar surface exposed to water. What about in the folded protein? What's going to happen to it? What's going to happen to its free energy and why? And what I'm going to tell you is that proteins fold just fine. I mean, they aren't as stable as it turns out. Okay, but they're not unable to fold from this type of substitution. But what problems might be introduced? Don't just answer my question, then I'll repeat it. The question is, what's going to happen when you take a tightly packed alanine and make it big? What free energy changes do you expect in the folded state, and why? Why would it be more favorable? Yeah, they can accommodate these things. Yeah, forcing it in there. Well, I mean, you don't have enough space, right, for a leucine. When you look at that structure, you say, there's no way a leucine's going to go in there, right? So, is that going to be a good thing? Favorable to jam a leucine into an alanine-sized space? Well, no, okay? I mean, this is just hopefully common sense, but maybe not. Okay, if you have a crowded space and you try and think about it, if you're in an elevator and you want to pack 3 more people on, because that's basically kind of what it's like, it's going to get a bit tighter in the elevator, all right? And that's what's going to happen inside the protein, except protein atoms can't overlap, and atoms aren't really squishable like people are, okay? And so things are going to have to move. There's going to have to be some movement, all right? And they're going to have to be pushed outwards. So that's going to cause what sort of problems, potentially? Yes, which you would call, which energy type would that involve? Well, what are the ways that atoms interact with each other? Yeah, van der Waals. So your van der Waals strain. What else? What other types of strain might be possible? Okay, besides van der Waals. Atoms don't like to be close to others, so what can they do to try and get out of the way of each other? Actually, we've already talked about how this can happen. What's another? So how can atoms adjust? They can move, away from each other to avoid van der Waals strain. They can do that just by moving, okay? But they can also do what? What are the other ways the molecules do to change their shape besides just simply moving? They can rotate, right? So they could be torsional changes. And we already know that most side chains are in good torsional position. So you probably have the potential for introducing also torsional strain by rotating away from that thing, okay? So definitely, yeah.
What about breaking bonds?
No. Okay, and the reason I say is bond energies are 100 kcals per mole or more. Okay, and we're talking about a few kcals, so no way, no bonds are going to be breaking. And I just want to repeat myself for those of you who are maybe don't remember I said this. Nowhere in this course are we going to talk much about bond breaking. Everything is non-covalent. Okay, all the courses we're going to talk about non-covalent, and they're roughly 10 times smaller to 20 times smaller than covalent interactions, all told. How would it do that?
By shifting other things around.
Okay, so let's talk about the general thing. Right, if you shift residues, then not only are you going to have a local issue, okay, but you're also going to be pushing residues that are already tightly packed against other residues. They're also going to have to readjust their positions. And that can interfere with a number of different things. Certainly can interfere with other van der Waals contacts. It could also cause, potentially changes in hydrogen bonds. But actually, what about unfilled space? You take a nice jigsaw puzzle, now you jam something into it, or a nice stack of blocks, and you jam something into it. The blocks are not going to fit together so well anymore. And in fact, you actually can end up with more unfilled space than you had before. So paradoxically, even though you're increasing the size of the residue, you actually can come up with more unfilled space because of packing problems. So that's what happens, okay? You have strain, and we talked about van der Waals strain and torsional strain, and there's also loss of van der Waals from moving things apart, and there's also cavity entropy. So in some cases you might be pushing too hard on something that causes van der Waals strain. In other cases you might be moving things apart because you're pushing on something else, and that causes reduction in van der Waals energies, favorable van der Waals energies, and maybe the introduction of torsional strain. Then finally you end up with more unfilled space. So now you have two different situations. You have an increase in free energy of the unfolded state and an increase in free energy of the folded state. Those are both moving in the same directions. The question is, generally speaking, which one particularly is bigger? And what I'm going to tell you is typically, most of the time these are destabilizing mutations. So I'm writing the range here of -1 to 1 to +0.5. This is stabilizing. That occurs in very, very rare cases where you can fill an existing void without introducing anything bad. The one example that I can think of is an RNase T1. There's this particular isoleucine residue, particular valine residue that happens to have a cavity right next to it perfectly so that isoleucine can fill that. If you convert that to isoleucine and fill that cavity, and it looks like it does it without any strain, then you do get actually about a kcal stabilization for doing that. Okay? So that can happen, but it is incredibly rare. Almost always you have the opposite situation where you're not filling space more efficiently, you're actually kind of disrupting it. And by the way, just for that RNase T1 example, it's interesting that other orthologs of RNase T1 do have, in fact, isoleucine there. Okay, so why it has a valine there, who knows? Okay, so usually the strain is much bigger than the change in hydrophobicity. But if you don't introduce strain, then you're at least very much getting the solvent transfer free energy advantage by increasing the free energy of the unfolded state and not changing the folded state. But that's not usually what happens. The folded state increases usually more. And like I said, up to 5 kcals per mole. There's one T4 lysozyme mutant, A98 to B. This is an alanine to valine change, causes a 5 kcal per mole destabilization. And it turns out that that's likely due to disruption of the salt bridge, of an energetically important hydrogen bond, because there's not that much steric strain. Okay, so let's look at a picture of one of these guys. So this is the same view of T4 lysozyme I showed you before. This is the helical bundle of the C-terminal domain. Again, these are the residues that are around in the structure. And what we're doing here is we're taking an alanine at position 129 and we're making it into a methionine. Okay? And right next door to this residue is our friend leucine 121 that we talked about before. Now, methionine is a much bigger residue, and these are really close together, so the net result of this is a very crowded situation. And that crowdedness is really exhibited in two different ways. One is that there are actually close contacts between this methyl group and that guy. They're closer than good van der Waals distance. The second thing is that this methionine is actually squished up, okay? Rather than being extended like most methionines are, maybe a little bit of a wiggle, it's squished up in a conformation that has basically never been seen before in a naturally occurring protein, okay? So that's clearly unusual. And then this leucine also itself rotates into an eclipse conformation, which we already know is high energy. So we have two very conformationally strained residues. Okay, they're pushing each other, and they have van der Waals strain. And in spite of that, the protein still has to pry itself apart. And that's evidenced by the fact, again, in this case, the green lines are outside the red lines, which means that the C-terminus is expanded. Not a huge amount. These are small motions, but increased cavity size in the interior. The naturally occurring cavity in T4 lysozyme is this yellow thing. It's always there. It's in the wild-type protein. But it actually gets bigger by about 24 cubic angstroms because even though you've stuck a bigger residue in there, it's pried the whole protein open a little bit. Yes?
So what's sterically clashing?
The methionine and the leucine residue. So the leucine at 121 is being smashing into the methionine at 129. And the methionine was the introduced residue. Okay? All right. So basically, you see it all here. You've got increased unfilled space, you've got torsional strain, and you have steric strain. Okay? This guy isn't that destabilized. It's destabilized by about 1.6 kcals per mole, 1.3 kcals per mole. But if you actually account for the changes in hydrophobicity, it introduces about 3 kilocalories per mole of strain overall. Okay. So we get into this business of packing. Okay? How well packed do things need to be happy? And so what you could do is you could say, well, I'm going to not worry about hydrophobicity changes. I'm just going to worry about shape changes. I'm going to take hydrophobicity out of the equation by changing leucines into isoleucines. These two residues have the same hydrophobicity. They have about the same surface area, but they're really quite differently shaped. So the question is, to what degree is the packing environment around a leucine adapted to be leucine-shaped, not shaped like anything? All right? So it turns out that that's usually destabilizing. So what's going on here is that you have similar hydrophobicity, so the unfolded state free energy doesn't change. But again, because you are packing a different shaped environment, you're trying to put a square peg into a round hole, okay, you get problems. And the problems are just the same problems that we talked about, the potential for the introduction of van der Waals strain, not packing certain volumes, because of course the shape of the residue is different. There might be parts that can't be accessed. All these lead to destabilization. So again, disruption of packing quality is almost always destabilizing, although there are certainly cases where it's neutral or even stabilizing. For example, that phenylalanine in T4 lysozyme we've been looking at all along, when that's changed to a leucine, protein actually becomes more stable. And that may be some evidence of strain. I don't know. But phenylalanine and leucine also have about the same stabilization. Stabilization is small. It's about 0.7 kcals. Okay. All right. So one question that arises then is it's really about filling space, okay, and how well do you have to fill space? And so there's a paper that I wrote, and I'd like you to read it if you get a chance. But it basically asks if you really look at two residues that are adjacent, one small and one large. You switch their volumes. What's the result of that? Okay, and the result, generally speaking, that comes out of it is that it's not only about hydrophobicity; it's also about packing things together well. But I think there's a better demonstration of that I'm going to talk about here. Okay, now these pictures often have not reproduced well, so I'm sorry about that. Things change with PowerPoint. So this is an old-style molecular diagram of really a bunch of T4 lysozyme mutants superimposed on each other. And what these mutants are is they're mutants that have basically been put through a process by which all 20 amino acids were allowed to be at 5 selected positions in the interior T4 lysozyme, and they're all residues that form one contiguous volume, basically. So we're asking, if I put all 20 amino acids there, how many different ways can I fill this space and still have a working protein? And so you can make libraries of mutants like that, although when this is done, it was a little bit trickier. And then you can use some sort of functional selection, which in our case was, this is a lysozyme, and you can make a bacteriophage dependent on the lysozyme, like we talked about before with T4 phage, but this is done with another phage. And you can ask, does the virus still replicate and it still get out of the cells. It still make plaques. And if it does, then it's functional. And then you can use the plaque scoring assay that I talked about before with halos to kind of get a better idea of who's more active and who isn't. And in general, these are the top 8 mutants that came out of the screen. Okay? And what you can see over the 5 positions is that there's definitely variabilities in what residues are allowed there. The first thing that should shine out in you here is that all these residues are hydrophobic, even though all 20 amino acids were allowed. So immediately speaking, to have a functional protein or a high-level functioning protein, you have to have all hydrophobic residues. And I think that kind of makes sense. All right? The second thing is that you'll notice that some positions are pretty invariant, like this one here, 149. That only took really for, again, highly functional proteins, either a valine or isoleucine. That means that particular shaped spot, okay, is really isoleucine or valine shaped. And about that particular spot, which happens to be right down here, you can't really see it, but most of what surrounds it isn't other residues. It just sort of is kind of bumping into a little bit into the phenylalanine, but for the most part, it's the main chain residues, the invariant parts of amino acids that are touching that volume. And so putting anything other shaped there would really disrupt a lot of the structure. And we know that that's a fairly sensitive site to substitution. Other sites, like these 3, particularly these 2, okay, can be almost anything, all right? Anything from alanine to tryptophan or alanine to leucine. So those are much more flexible positions. And then there are intermediate ones like these 2, where you typically have, for the most part, although you do get some other residues, when they get smaller, the protein's not as happy. And here you pretty much have large hydrophobics. And again, this has to do with the fact that this environment isn't really able to be reached by any of these other residues, so you need to have something big to fill all the holes. Okay. So the second question is, okay, it looks like a lot of things are tolerated here. Why? How did that happen? Okay? And again, you can see in some cases you have a large number of residues tolerated, and others not so much. One thing I hope you notice is that these residues actually aren't really in the same positions. If you look at their alpha carbons, they're all shifted away from each other after superimposing. And what that means is that the rest of the structure has moved in response to these. Yes?
I had a quick question about what do the dashes mean?
That means it's the same as wild type.
Okay.
Okay? So the wild type is across the top, and then the dashes are where there's no, it's valine or phenylalanine. Okay. So let's look at how proteins adapt to when you start messing with their interiors. So really, again, sorry about the poor reproduction of these. These are similar pictures that I've showed you before, at least this one on the left is. And in green is a mutant protein that has 5 substitutions. Okay, all 5 residues have been substituted. And in red is the wild-type protein. And hopefully what you can see is that for the most part, the structure of the protein hasn't been hugely altered by this, but that there are definitely positional differences. First, if you look at the individual side chain conformations in this particular case, they more or less trace along the same position as the wild-type protein. Okay, the same as that wild-type amino acid, they more or less trace along the same position, but overall they've been shifted in position. And that's because in this particular case, this volume, increase in volume due to all these residues is about the size of adding a whole new tryptophan residue to the interior of the protein. So the proteins had to absorb a volume increase about the size of the tryptophan. And it's done it by swelling up. Here you can clearly see that the green lines are outside the red lines. Okay? That the backbone is swollen up. Okay? And it's done it kind of a little bit all over the place. And of course that amplifies the situation. However, that's not good enough in some cases, like here, where this residue has moved about 2 angstrom away from its original position. Okay? And that's because this helix has entirely rolled, okay, to carry it. So a small roll of the helix, maybe 2 or 3 degrees, accounts for a big positional change in that methionine compared to where the leucine was. So that's how space is made. And what you can see in this particular case, almost all the changes are pretty subtle in terms of where the side chains are going, but that the backbone has absorbed quite a bit, okay, of the volume increase just by swelling up. Now the one next to it is really different, okay? So this has actually the same exact volume change as this one. It has the same stability as this one, but structurally what's going on is a lot more dramatic. So here, all the volume change is essentially concentrated in 3 substitutions, primarily in this alanine to tryptophan substitution. So again, about a tryptophan extra of volume. And in this case, you have some pretty profound situations. First of all, the backbone movements are quite a bit larger. It's really squished the backbone out of place almost by an angstrom in some cases. This isoleucine is taking on pretty much the same shape as the original leucine, but it's shifted about an angstrom and a half away from its original position. And this methionine, if it traced along the leucine's conformation, it would bang into this tryptophan. There's not enough room for it. So this guy has to swing out of the way. But of course, when you have a tightly packed residue and it has to swing out of the way to make space, it's tightly packed, so it's going to meet other residues when it tries to rotate. And in this case, it could change because its only neighbor in the way was this phenylalanine, shown in red in the wild type and in green. And this phenylalanine has conveniently swung out of the way because it is at the surface and there's nothing restrained in its position. So what you have is kind of a revolving door in this case that allows this methionine to find a new position where it doesn't collide with the tryptophan. If it didn't have that, I'd expect the protein to be much more destabilized. So I guess what I'm trying to tell you is that proteins can subtly change their shape enough to accommodate amino acids, or they can do more radical things and not incur extremely large stability changes. Now, in both cases, these guys are destabilized with respect to wild type, and they've absorbed an extra tryptophan's worth of hydrophobicity. So clearly, there's a bit of strain going on here. Okay, there's no doubt a bit of strain. So the tryptophan alone, increase in hydrophobic surface should increase the stability if it doesn't cause strain. But the fact that these are slightly destabilized, 1.3 kcal per mole destabilized, and that's because there's strain introduced by these changes. Okay. So kind of the take-home from this sort of study is that basically, or from all the things I've told you, is that generally reducing hydrophobicity is a generically destabilizing influence of proteins. Why? Because you're varying less hydrophobic surface, and you're also creating less filled space in the folded protein. Basically, if you mess up the packing by either overpacking or underpacking it, you're also going to have stability changes. And then, ironically enough, overpacking has some of the same consequences as underpacking, with the addition of introduction of van Waals strain and torsional strain. Something that I didn't tell you about is that we never recovered a more stable mutant, than the wild type. Now, that could have been due to statistical sampling issues, but generally speaking, when people have done these type of experiments before, they get very, very few stabilized mutants. Almost always, you get something destabilized. But that tells you that the wild type protein, the one that's been through an evolutionary process, is near optimal stability, at least within a few amino acids of its sequence. So, but the other thing, this is the good news for evolution, because if it was so tightly packed and so perfect that it couldn't stand any substitutions without falling apart, that would be bad for evolution. So there are many tolerable ways and compromises to get a reasonably stable and functional protein. Okay. All right. Are there any questions on that? I do expect you to kind of understand and deal with problems that are like this. There are problems in the problem set, and when we get around to having a midterm again, very soon, then we'll have also posted sample problems. Yes?
You mentioned how the wild type is the most optimal stability, but in the graph it shows like the delta G as being negative for all of the mutants.
Yeah, negative, no, sorry. My apologies. You mean on the chart? So once again, because this paper was published at a time where the convention was for unfolding, those negative values are actually destabilized. Thank you for reminding me to say that. So yeah. Let me go back and just point that out. Okay, these numbers are negative because those are delta G's of unfolding. Okay. Thanks. Okay. Any questions on that? All right, let's shift gears and start talking about polarity. Okay, because we talked about packing and hydrophobicity. So we know that the hydrophobic core is really supplying this nice template of residues that fit together rather well with low strain energies, large hydrophobic surfaces, to stabilize the protein. But then the question is, we also do see polar residues in the encoding interior. And so one of the questions is, well, what are they doing? And then the second question is, how costly is it to do that? Right? So what I'd really like to do is I'd like to be able to do an experiment where I introduce a polar residue into the protein interior, and see what the effect is only of polarity, not of other things. Can you think of a substitution I could do that would convert a non-polar residue into a polar residue but not change anything else about it except its polarity? Or at least not hugely change it? Are there any amino acids that have the same shape but different polarities? Can't think of any? You've got to work on those amino acids.
Alanine and tyrosine.
That's an interesting choice. Tyrosine is a hydrophobic amino acid, is more polar, but it is also sterically different. Okay, so it has the hydroxyl group. So that's a good idea, but I think there's a better one. Yeah. Valine and threonine, perfect. Okay, because valine and threonine are both beta-branched amino acids. The only difference is one has a methyl and the other has a hydroxyl. It's not exactly the same, but it's as close as you're going to get. So what happens if you take buried valine residues and change them to threonine? Okay, so let's go back and do our thought process. What's going to happen to the unfolded state free energy when I take valine and turn it into threonine? Which one interacts more favorably with water? Threonine. So what's going to happen to the free energy of the mutant compared to wild type in the unfolded state? Just the unfolded state. It should go down, right? It should become more favorable. Putting a polar residue in, make hydrogen bonds, less hydrophobic surface, and so forth. So you expect that to go down. Now the protein folds up, and we're talking about the folded state. This is very valine. Sterically, you haven't done anything bad. You really also haven't created cavities. So what do you think the free energy consequences is going to be for the folded state? Is it going to go, is it less favorable to do that or more favorable? And why? Excuse me. What do you think? Well, okay, this is all about chemistry, right? So we're taking a hydroxyl group from water and putting it into the middle of the protein. What's different about those environments? The same? What's different between water and the interior of the protein?
The interior is hydrophobic.
Yeah, interior doesn't have hydrogen bonds. Okay, so now you're taking a hydrogen bonding group out of water, where it likes the hydrogen bond, and now putting it in the middle of the protein. Is that going to be a good consequence? Is that going to be favorable for the unfolded state free energy, or sorry, for the folded state free energy, or unfavorable? Unfavorable. Okay, free energy is going to go up. That didn't take a lot of, I don't think, brilliance. You're taking a hydrogen bond and you're burying it. So basically, if you have a dipole, and we already talked about this dielectric constant business, and so we can put it in terms of that. You're taking it from a high dielectric environment, which can adjust itself to satisfy that dipole, and now you're putting it in an environment that can't really do anything. All right, and so you definitely would expect to pay a price for that. Another way to think about it is you're stripping the hydrogen bonds off from water, and now there's no hydrogen bonds. That's not going to be good either. Both of those are the same thing. So its free energy is going to go up. All right? And so, generally speaking, these are destabilizing. However, when Michael Blaber did a series of these valine to threonine changes, he found that the free energy change, again, was variable. And, that there were some that had almost no change and some that had a lot. And so the question is, what's different about these mutants, the ones that have the small change in free energy versus the ones that have the large difference? So you solve the structure and you look at it and say, oh, now I can tell. So what do you think are the potential consequences, okay, the potential responses of the protein structure to burying a dipole? What possibly could be happening to give you those different changes in stability? It's clearly not steric, right? Because, sterics are the same. What could be different about those mutants? So in the plus 1 kcal per mole change, do you think that hydrogen bond is just sitting there unsatisfied? Maybe there's a way that could be satisfied. Okay, so let's think. So this is how you kind of walk through this. You start. Well, what needs to happen for there to be less than expected stability change? And by the way, roughly speaking, 2 kcals per mole is on the outer edge of what you'd expect just from changes in solvent transfer of the energy. Okay, yeah. So water might come in, okay? That does happen, all right? And we'll get back to that. What's another thing? You mean make something else and give it a hydrogen bond? Like phenylalanine or something like that? It's possible. It's possible. It's hard to see that crystallographically, so I don't think we'd be able to know that. But what I can tell you is that I think there's a more, maybe less obvious explanation. Okay, yours is a subtle one, but I think there's a more obvious explanation. So one of the cases that drags a water molecule in. What else? just stick with it. Finds a new partner. Okay, yeah, finds a new partner. Okay, and that can happen. Remember, there are carbonyl groups and amide groups in proteins, in alpha helices. Okay, it turns out if you have a glycine in one position, you can actually access the carbonyl hydrogen bond, no problem. So, or somebody still hasn't mentioned what possibly could change. Okay, so generally, I think that's another strategy is to find another hydrogen bond besides water from the protein. And what are the ways you can find it? Well, one, there might actually be an existing hydrogen bond already that it can take advantage of. What's something else that could happen to give the new hydrogen?
Hydrogen bond to the backbone.
Okay, that's right. So that's an existing hydrogen bond. And that can occur with no structural changes, right? It happens to be put next to something that has a hydrogen bond. That's also been seen. What else? Yeah.
Maybe a hydrogen bond residue swings to nitrogen.
That's right. Hydrogen bond residue could actually change its position. We've seen that positional changes are possible. They're not super fatal. But it turns out that in some of these cases, that's what happens. So there are three outcomes, all right? So the one outcome is that nothing happens, okay? And those are rather destabilized, but they're not the worst, okay? And in those cases, it's just probably because we don't understand the electrostatics inside of a protein. Maybe there's an electric field that happens to align with that dipole, okay? The second thing is that the side chain finds a partner. Now, either it does it by finding a main chain atom, like an alpha helical one that somebody said, or a nearby side chain actually can rotate. And that was observed. Both of those were observed in structures. The last one, which is the most destabilizing one, is where it drags a water molecule. That's the 3K calcimol one. And then you kind of wonder, well, wait, it's got a hydrogen bond. Why is that so costly? Okay, why is it costly to drag a water molecule? So we can sort of dissect it first and think about what are all the entropic and enthalpic components that occur when you drag a water molecule. What's not good about pulling a water molecule into the protein?
You're now surrounding the water molecule with the non-polar. It can only make the one hydrogen bond and nothing else.
Yeah, and you're reducing the number of possible hydrogen bonds. What I'll tell you is in the structures where that was seen, there were at least one other hydrogen bond, okay, available, again, from an existing donor or receptor that was there. So yeah, pulling one, stripping off waters and reducing this amount of hydrogen bonds, which is like 3.4 in water, hydrogen bonds down to 2, that's definitely going to be a loss of energy. What else is bad about this? Very good. What else is bad? Yeah. Yeah, so in these cases, the water entered a kind of a void that could accommodate it, so it wasn't necessary to do that. What about, we've been talking about enthalpic costs. What about entropic costs? Remember, restricting the motion of anything is entropically costly. So taking a water molecule out of solution where it's full translational freedom and bringing it into the protein is costly. Binding anything costs you entropically. Okay? So that's another explanation. And so then the question is, well, okay, if that's so costly, why did it do it? Okay, and what's always the answer for why things happen? Well, evolution is one. In this case, it's a non-evolutionary question, but this is even a more obvious answer, okay? When something happens and you can't explain it, what's always the fallback? It doesn't inform you any better, but at least, it's something that you realize. And again, you guys may say, well, what do you mean by this? Well, what I mean is that I think people think that if things happen, that aren't good, then that's somehow, unusual or weird. But you always have to ask, what happens if it didn't happen? That's really the question to be asking. Why are we seeing something that's clearly not favorable to do, stripping water off a water molecule and burying it in the core of the protein and immobilizing it? That's clearly not a good thing to do. But not doing it was clearly worse. In other words, that hydrogen bond was in a really bad place. It wasn't going to get any satisfaction from its locale, so it had to pull a partner in. That's the indication. The indication is it was better than the alternative. That's always the answer. You see something happen, and it seems like it's bad, well, the alternative was worse in chemistry. Atoms don't have choices, okay? We do, but they don't. They got to do what's best. Okay. Is that clear to everybody? So hopefully what you've gotten from this is, first of all, understanding how polarity mutations can affect stability, which is pulling, making the interior non-polar, or making it polar is not a good thing. But also, how we think about the forces that are involved and the things that you have to consider. You have to consider entropic changes, you have to consider changes in hydrogen bonding, van der Waals contacts, and you also have to consider the amount of space that's there. This is the chemistry part of all of this. Okay. Let's do something really crazy. Let's take a leucine and make it into an aspartate. Now, I'd like to be able to say that this is an isosteric substitution, but it's not. leucine's got a branched beta carbon or gamma carbon. It's tetrahedral. Aspartate has an sp2 hybridized gamma carbon, so they're really not the same. But really what we're after here isn't so much the steric differences, but what about putting this charge thing into the middle of a protein? I'm sure you guys can answer this question. What do you think the consequences of that sort of mutation are going to be? It's taking a hydrophobic residue that's buried in the protein and making a charge. Is that going to be favorable? No, I mean, we already know from just putting a hydroxyl group in place of the methyl group that that's not too favorable. This is going to be really bad. Why? Because charges, well, they're more polar. And they're going to get less satisfaction. So, yeah, you're going to have two things. You're going to have even a greater drop in the unfolded state free energy because the charged residue interacts better with water than leucine by a lot and more than a hydroxyl group. And you're going to have really increased free energy of the folded state because barium charge in a low dielectric medium, where water can't get to it, is really, really destabilizing. And these are very, very severe mutations. 2 to 8 kcals per mole for all the times that have been done. Again, variable. Because none of these are leucine to aspartate changes. Actually, they're introducing some sort of charged residue into nonpolar space. The one that's 8 kcals per mole is turning a buried methionine into a lysine. And a structure could actually be determined of that protein. So even though it was 8 kcals per mole down, it was still forming the right folded state. Okay, so yeah.
So, but still, however, these would still occur. There's still something in like delta G, or does it all depend? Like, is this just figurative? I mean, here we see that the folded state does have a lower free energy, so we would say.
No, the folded state of the mutant has a higher. You mean lower overall?
Overall, going from unfolded.
Yes. So we're talking about a single substitution. Okay. If it changes that much, then the protein would fold, right? Okay. So the K is still favorable. It's just a few, 2 orders of magnitude. Does that make sense? Yes. Okay. Actually, about 6 orders of magnitude. Okay. So, clearly that's a bad thing to do. But then the question is, this charged residue, first of all, when it's buried, is it charged? Okay. And what's the cost of burying a charge versus burying an uncharged residue? And what does that do to its proton affinity? So one of the questions we might ask is, what's the effect on that residue's pKa? Because that's telling us about how much it wants to be charged. And then, how does that result in a stability change? Presumably, there'll be a difference between being charged and uncharged. How can we know what the effect on stability is? And the reason I like this particular problem is it allows us to start talking about this process called linkage analysis, which is a way of asking, if you have 2 equilibria that are intertwined, how do they affect each other? You see this all the time. You see it in redox equilibria inside of cells. You see it in coupled enzyme reactions. You see it in trying to bury polar residues or charged residues inside of proteins. And so to do this, we have to kind of do the linkage thing, and that involves thermodynamic cycles. I think what I'm going to do is I'm going to take a break now, okay, and then we'll get back to this and finish up with it. Okay, so let's take a 5-minute break, so 3:16. So, this linkage business, okay, involves, as said, talking about what happens when you have 2 intertwined equilibria. And so, for example, we're talking about 2 equilibria here. We want to know what the stability change is due to burying the charged residue, and we also want to know what the effect on the residues of pKa are. So we're talking about an ionization equilibrium, solution of proton, that's why we use the pKa, and we're also talking about folded equilibrium. And it turns out to kind of solve this problem, we can draw a thermodynamic cycle. And remember, thermodynamic cycles, we'll get to them later. So we can start with our unfolded protein that's protonated. It can be ionized. We also have the folded protein that can be ionized. Those are 2 different things. And so one question we might ask is, what's the difference in ionization of the folded protein versus the free energy of ionization of the unfolded protein? Okay? The second thing we're asking here is, what happens when you fold the protein up when you have a protonated form versus folding up the deprotonated and charged form? This difference is really the free energy cost of burying a charge. Okay? And that's kind of what we'd like to find out about. So I think intuitively we can understand how a buried charge would contribute to stability. Well, and now what we're doing here is, rather than talking about a mutant and a wild type, we're talking about neutral and charged versions. And generally speaking, we think of the free energy of the interaction with water being stronger when we charge the residue, so deprotonated in a solution, okay, should be a favorable thing to do. However, in the folded state, things are a little bit different. we take a polar group, which is the carboxylate in this case, with a proton on it, and then we charge it, we expect a big increase in free energy. Why? Because varying the charge is even a more severe problem than varying the dipole. Okay? So intuitively, we definitely expect that the charge is not going to be good for stability, just based on this kind of argument. And in fact, the delta G of the effect on protonation, effect of forming a charge on folding, which is what this is meant to be, is going to be the delta G of folding of the charge residue minus the one of the neutral. So we can get after this by the thermodynamic cycles. So in general, for thermodynamic cycles, if you can draw a closed cycle, in other words, you can connect the dots together, so you go all the way around in the circle, what do you know about that? Okay, why do you want to do that? What's the purpose of doing it? What's the purpose of creating it? Yeah.
Free energy is a state function.
And so?
So, you get back to the start and you've done the same amount of electricity, free energy has to be the same.
That's right. So in other words, if you go around a circle, the free energy change for all those processes has to sum up to be zero. Okay? And that turns out is enough to be able to make this a tractable problem. If you don't close the cycle, then you can't use the circle. So it's basically giving you an algebraic tool, okay, to relate two different equilibria. So when you do this, what you find is that basically you can't any longer consider them either interdependent. So let's go through that. So you start with the idea that, again, as the gentleman said, delta G is a state function, which means it doesn't matter how you get places. If you end up in the starting place, end up in the place where you started, that has got to be free energy change of zero because you haven't gone anywhere. You may have individual free energy changes in your path around to get there, but overall those have to be sum up to be zero. I'm going to tell you right now that for this to work, you really need to watch your signs. Okay, and what I mean by that is that delta G's have conventions. Okay, we name delta GF. I'm saying that point that the delta GF is going from unfolded to folded. Okay. If I meant to be delta G of unfolding, I would reverse that. Okay, and when you're summing these delta G's, you have to make sure that you're summing them with the correct sign. I'll try and show that to you when we do this example. Okay, so here's our thermodynamic cycle for folding, the effect of folding on an ionizable residue, on a carboxylate. And again, we have two processes that involve ionization, and this is related to the loss of a proton directly, because you lose a proton, you gain a charge, and we're positing that maybe these are different. Okay? And likewise, we have folding free energy differences between a neutral and a charged form. So, what we'd like to do is pick one direction in this cycle and basically determine how we sum up all the delta G's and then set those to be equal to zero and then use an algebra to separate terms. What we'd like to do is end up with having all the folding terms on one side, all the ionization terms on the other. And no matter what equilibria you choose, you can do this. Okay? And the results are kind of interesting. So, I pick a direction. In this case, it's clockwise, but if I did it counterclockwise, it would still work. And so let's just go through our sum. So if I start here, my first delta G is delta G of folding of the carboxylate form that gets added. The second thing I do is I deprotonate the folded forms. That's a delta G of ionization of the folded form. That's going in the right direction. I add that. Now I'm unfolding the ionized protein. That's the opposite direction of the delta G of folding. Why? Because that's our convention. So I'm going from folded to unfolded, so I put a negative sign in front of that. Okay? And then finally, I'm going from into the unfolded charged form to the unfolded uncharged form. That's the opposite of ionization, so I put a negative sign on that. And these all sum up to be zero because I've gone all the way around the cycle. Is everybody following me here? Okay. Because on your exam, I'm going to tell you right now, you're going to have to do this for binding and folding. Binding of a ligand and folding. Okay? So pick a direction. We did it. We make the sum. And now we do the algebra. Okay? Well, this is negative, this is negative. I want to keep ionization on the left side and put folding on the right side, so I'm going to add this guy and subtract this one. That's what I get down here. So the free energy folding difference between the charged and uncharged states is what I have on this side. And on this side, I find that, again, I'm left with delta G of ionization of the folded form minus delta G of ionization of the unfolded form. And what this is telling me right here is that this is the change in stability. So what I've done, just to be clear, is I've actually flipped these. Sorry, I didn't like that arranged. I just changed sides. I can do that without changing anything. And when I do that, I find that the change in stability due to ionization is going to be exactly equal to the difference in ionization free energies between unfolded and folded. They're not, you cannot disentangle them. They are exactly the same. So how do we do this? Well, this is the contribution of the charge to stability. That's what this is saying. Okay? And this is the difference in free energy of ionization, which it turns out is related to its pKa. Because remember, pKs are about losing protons. When a carboxylate loses a proton, it becomes charged. So therefore, its delta G of ionization is minus RTln Ka. This Ka is the dissociation direction. If we substitute pKa equals minus log Ka, then we get 2.3. That's the difference between a natural log and a log base 10 times RT times pKa. If I'm talking about this difference, I can factor all these out, and it's 2.3 RT times the delta pK. In other words, the delta GF of ionization, the free energy change and folding due to ionization of the side chain, is related exactly to the shift in pKa going from the unfolded to folded form. So if I can measure my pKa's, I don't have to determine this, which sometimes is actually impossible to do. A lot of times you can't melt proteins under conditions where one side is deprotonated and the other side. When one form is protonated and the other one's not. It's just not possible to do that. But you can get pK shifts. So in other words, there's a direct relationship between the shift of the pK of the side chain and what it does to stability. Which, I don't think that's obvious, but there it is. So many people, well, what do you mean by pK shift? Well, you have to have then the pKs of the folded and unfolded forms. Where do these come from? Okay, and I actually have told you before, but I'll remind you. The pK of the folded form you can get from NMR. We talked about this. Okay, when you titrate a residue, its MI chemical shift changes, and so you just follow the chemical shift change with pH, and you get a nice titration curve, and you get a pK from that. So that's what people do. The pK of the unfolded form is actually harder to experimentally directly determine, because then you have to add urea and all this sort of stuff, or heat it up, and that doesn't work very well. But it turns out that we have lots of information about the dissociation of side chains in solution of peptides, small peptides. And so we know that the pKs generally don't move around that much. There are some nearest neighbor interactions, but for the most part, they don't move around that much when they're in water, because they're in a water environment in all cases. And so this is estimated from something you would look up in a table, what we call the normal pKa of a side chain. So that table I told you about before would be the source of something like that. Now, before you get concerned on an exam, I'll make sure I tell you exactly which pKa I want you to use. Okay. All right. So that's the case. So like I said, in other words, there's a direct relationship between the pK shift in the side chain and the stability contribution from the charge. So that might be a little bit hard to understand. Why is the stability change directly linked to a change in ionization free energy? It's not obvious that should be the case. Although chemistry and math tell us that it has to be that way. It's not necessarily intuitive to understand that. So does anyone have kind of an idea why they're the same? Let's pick it apart. Let's look at what's going on in each case. So in the case of the charge forming inside the protein, okay, what we're asking is, what's the difference of interaction of the protein with that charge, right? And that's what really is reflecting the stability change. There's a charge or a not charge. The protein interacts with them differently if there's going to be a stability change. And that's due to the influence of the charge on its environment, right? That's the stability part. The environment is the protein. On the other hand, pKa is really about what? It's about the relationship of that residue to its environment. Okay, what determines the pKa is how well solvated that ion is going to be. Okay, or what kind of influences there are to stabilize the ion that you're going to form. That's what determines how hard it is to dissociate them. And some of those are intrinsic to the molecular structure, and some of them have to do with the environment. So really, the pKa is reporting to us how the environment is influencing that charge. And what I'm going to tell you is those are two sides of the same coin. On the one hand, you're monitoring what's going on in the environment and how it's being influenced by the charge by the folding free energy. And when you're looking at pK, you're asking how's the environment influencing the charge, and the pK is giving you a readout of that. So essentially, if there's no pK shift, there's no interaction with the environment. That's what it's saying. Or no interaction difference between going from a solvated state to being in the middle of the protein. Okay. So That's the deal. And that's true for all of the linkage equilibria. They're really just giving you two different ways of looking at the same interaction. It's a two-sided interaction. There are two different measurements you can make that give you the same number. Okay, so in terms of how we interpret these sorts of things, basically, if the folded environment of the protein is more favorable than in water, which is not the case that we just talked about, but there are buried charges in proteins, and we actually know that they are favorable for folding. Okay? And they have pK shifts that reflect that. So basically, if a folded environment is more favorable for the charge than water, and what that means is that there must be something in that environment that's better than the hydrogen bonds of mobile water. And what you will see is that is the fact the protein is supplying lots of good hydrogen bonds to that. It's created a binding site, if you will, for that charge. All right? Then the pK is going to shift towards ionization compared to the unfolded state. Why? Because it wants to be ionized more in the protein than in water. And that's because the protein has created this beautiful environment for it. So if you're a glutamate or an aspartate, to be shifted towards ionization means your pK will decrease. It's easier to lose the proton, it's easier to become charged. So you need to understand this relationship between losing a proton and charge, because that's what we're trying to learn here. For arginine, lysine, and histidine, these become protonated these become charged when they have a proton on them. So losing a proton, they become neutral. And so therefore, if you're shifting towards ionization, it means it should be harder to lose that proton. The pK should go up. So I should be able to give you a pK shift in a residue, comparing unfolded to folded, and you should be able to tell me whether that charge is good for stability or not. Right? So what examples do we have of that? We have salt bridges, which we'll talk about. We have N-cap and C-cap residues, which we'll also talk about. Now, in the case that we just talked about in terms of the example, if the folded environment is less favorable for the charge of water, i.e. the center of a hydrophobic part, then you expect the pK to shift away from ionization. And that means for glutamine or aspartate, the pK will increase. And for lysine, arginine, the histidine, the pK will decrease. That's an unfavorable contribution to stability. What examples are there? Well, buried charges. Okay, if we introduce them synthetically, it's definitely bad for stability. Proteins already have charges that are buried that aren't unsatisfied in catalytic clefts. And that's actually on purpose. We'll talk a little bit more about that. Or if there are two neighboring charges, again, in the catalytic cleft, those can be actually unfavorable for each other for stability. Okay. The last thing I want to kind of remind you of is that for each change in pK unit, so if you have a pK shift of 1 pH unit, that corresponds to a 1.4 kcal per mole or 5 kilojoule per mole change in stability. Okay? So there's an easy thing to look at. Look at the pK shift multiplied times 1.4, and you get the change in stability, and then the sign, of course, will depend on whether it's favorable or unfavorable, which you can determine. Okay, we'll do a couple of these. Okay, so where are the favorable polar and charged interactions in proteins? We talked a little bit about the fact that in alpha helix you have satisfaction of hydrogen bonds in the middle of the helix, but at the end you have 3 unsatisfied amides, and the N-terminus, the C-terminus with 3 unsatisfied carbonyls. That's actually a lot of charge. That's basically about 0.6 on one side, plus 0.6 on one side, and plus or minus, 1.2 on the other. That's a lot. So what happens is that the protein supplies hydrogen bonding groups to make those hydrogen bonds. Those are called capping residues. And when they're on the N-terminal side of the helix, it's called the N-cap. When on the C-terminal, it's called the C-cap. That's one place. The second thing is that all protein structures, and you will look at these when you look at your MAXI project proteins, I hope, have fully buried ion pairs that are hydrogen bonded to each other. Positive residue and negative residue form a hydrogen bond, and they're completely buried from water. They may have other polar residues around them, but those are completely sequestered from water. Every single protein has them. Okay? And they're definitely favorable for stability. And so related to these salt bridges, these might be just a couple of guys. These also might be part of a much larger buried hydrogen-bonded network in proteins. So again, all proteins of any reasonable size, you'll be able to find a set of residues that are charged or polar. They're completely buried, and they form a network of hydrogen bonds, often over a fairly large expanse of the protein. Okay, so let's talk about helix caps. So if you look at a protein structure, I guarantee if you do this, and you look at the N-termini, all right, you will see one of several situations. You will see a residue there that is making a hydrogen bond of some sort, or there'll be a potential for a water molecule to go there and do it. So it turns out that for helix caps, okay, the end cap, there's actually a specific position relative to the first residue that has a helical phi side that is actually called the helix cap position, because that's where amino acids that make these are positioned. Those are called secondary end caps, meaning that they're part of the secondary structure. They actually can be seen as part of the unit of the helix. So they're related to the sequence in a very specific way. It's the so-called N-1 residue. It's the residue before the first completely helical phi side. And these guys are almost always aspartate, threonine, asparagine, serine, and glycine. These guys, I think, are fairly obvious, okay? They have hydrogen bonding groups that can accept hydrogen bonds from the end cap. From the N-terminal amides. Now, why glycine? I think I gave it away. Glycine allows water to get in there, okay? Alanine will not. Alanine will not allow water to get in and do that, but glycine will. You often will see glycine at that position. Okay, particularly if the helix is on the surface where water can access. Okay? On the C side of things, rarely do you have secondary hydrogen bonds, but you still have something like a capping residue, asparagine or histidine. These are side chains that can donate a hydrogen bond to the C-terminal residues, and it's the last residue, it's the residue after the last helical segment or one more than that. And what happens is that essentially the side chain takes along the path that the helix would be taking, and in fact the main chain goes off in another direction. I think I talked about that when we were talking about beta strands as well. I guess you could call them helix breakers, but not in the sense that we normally think about. They're really sort of, okay, I'm going to add one more hydrogen bond before I get out of here. So those are something you can actually see in the sequence, and they do have predictive value, so often asparagine and histidine. But they can also be tertiary, meaning that they come from completely different parts of the structure that you wouldn't be able to predict just by looking at the sequence. They might be 100 amino acids away, something reaches over and makes a hydrogen bond with either the C terminus or the N terminus. And so pretty much everybody who's a H-bond acceptor can be at the N cap, and anybody who's an H-bond donor can be at the C cap. So it turns out the most common capping residue is aspartate. I'm sure in your proteins, if they're of any size, you'll find at least one of these, if not multiples. Aspartate is twice as likely to be there than anywhere else in the helix, so that's, I think, pretty significant. So one of the questions is, why is the charge favored over other things? Is it stabilizing, and how much? And so we can ask this question in a couple of different ways. We can ask what the effective mutations are that remove that charge but change little else, or we can certainly look at pKa's. Okay? So linkage is at the rescue again here, because what we'd like to be able to do is to do an MR experiment, but sometimes you can't do that, and so we'll do mutational analysis. The basic idea here is that essentially changing an aspartate to an asparagine is comparable to basically protonating that hydroxyl group. We can't force a proton on there and glue it there, but we can certainly make the residue something that can't dissociate. They're not exactly the same, but this is a decent proxy. So then it follows that basically the difference in stability of these, the mutant versus the wild type, is going to be roughly equal to the free energy change you'd expect due to the charge. Okay, that's the expectation. And so this is like an analog sort of situation. And so what's the result of this? Well, the typical delta pK values from NMR for these guys, type of residues, is about 0.5 to 1 pH. Okay? So in terms of what this means, is it means that they're negative, okay, changes, so the pK drops by that much. That means the environment in an end cap, okay, is better for an aspartate than water. Okay? Better for an aspartate. Why? Because it's got 3 hydrogen bonds pointed right at it in very specific geometry. If you make a mutation of an end cap to aspartate to asparagine, again, this was done in a series, you get pretty much 1 plus or minus 0.5 kcal per mole stability change, as long as that's the only thing that residue is doing. Okay? If the residue is doing other things, then you're disrupting multiple stuff. And that's pretty much what you expect from the pK changes. So essentially what this is saying is that there's a hydrogen bond donation from the end cap, but there's also a charge donation. Okay, the charge does something extra. And basically the electrostatic effect of the charge is favorable. The hydrogen bond itself is worth about another kcal per mole. That's what you get from comparing the asparagine to an alanine mutation where you can't make the hydrogen bonds anymore. Okay? So overall, each end cap conceivably is worth 1 to 2 kcals per mole total energy compared to alanine. Okay, so that's capping residues. So that's favorable. Let's talk about something that's unfavorable. okay, which is our friend, this catalytic residue. So here we have a glutamate at position 11 in T4 lysozyme. When the protein folds up, it's basically in the active site cleft, okay, and it has a perturbed pK. Its pK has gone up. It's gone up by 1 pH. And that is roughly equal to about 1.4 kcalmol destabilization to having that charge there. Okay? Now, why is it like that? It's because when you're in a cleft, it's hard to solvate something properly. Okay? It's hard for water to arrange itself around, less good solvation, higher pKa. Why does the enzyme do this? Well, this is a catalytic residue. This residue is directly involved in actually acting as a nucleophile to cleave the saccharide chain. And so, and it also acts as a base at another point. So to enhance its basicity and nucleophilicity, it's been necessary to tank up its pKa. Okay, and I think that's the best thing. That's typical for catalytic residues. Typically, when you have catalytic residues, they have unusual pKa's. Doesn't mean if you have an unusual pK, you're a catalytic residue, but and the reason is, again, the environment is not so great for it. If you mutate catalytic residues, they're usually stabilizing. So in this example, turning glutamate into glutamine, you get 1.2 kcals per mole, which is roughly equal to the solvation energy you guess from pKa. If you make it into an alanine, you get a little bit less. I don't know why that is. That's probably just a bit of noise. And then if you change it into a phenylalanine, you actually get an even greater stabilization. Why would changing that residue to phenylalanine, something hard, hydrophobic, be a stabilizing influence? What is that phenylalanine residue doing that the glutamine isn't? So remember where this is. Yeah, so you're in a cleft, right? And you're sticking something in there that is, in this case, filling up the cleft. Okay, you're filling up, you're reducing the exposed surface area, you're expelling water molecules, you're making Van Hoes. Okay? And so that gives you even more stabilization. So these are stabilizing influences. Okay? And like I said, in general, if you mutate catalytic residues, you almost always stabilize the protein. Not a great way to do it, right? Because you lose function. But you definitely get stabilization. So it turns out that substitution, as I said, of functional residues is often stabilizing. The question is, why? I'm going to kind of take a step back. There's sort of a passive explanation. Whoops. The passive explanation is what? Well, look, that residue is not optimized for stability. It's optimized to work, to do the catalytic function. And so, of course it's not the best residue there. That's one explanation. Call it a passive one because it's basically saying, well, it doesn't have to be bad for stability, but it just happens. A kind of bolder explanation, which I think makes more sense, is in fact it has to be destabilizing by definition. So why do I say that? Why would I say, for a catalytic residue to do its thing, it needs to be inherently destabilizing for the rest of the structure? Why would I say that? Except I'm insane.
Defines a ligand that's the most stable, so you want to be unstable until you find some medium to find.
Okay, so what you're saying in the more general case is that for a catalytic residue to do something, it has to interact with something else that's not always there, like the substrate. Okay? And if it's already tied up and satisfied in its interactions, it will not have anything left to interact with the substrate. Okay, interact with whatever it's interacting with. Unsatisfied interactions are what drive catalysis and binding, because if they were satisfied, nothing would happen. So the best protein stable molecule would be roughly spherical with no unsatisfied interactions. What would it do? Nothing. It would sit there. Okay? Because it's already happened. It's kind of like, I already have enough friends, I don't need any more friends. Okay? Whereas, if you're kind of feeling a gap for friendship, you're going to want to really go out and get some friends. Okay? And that's the way to think about catalytic residues. They're looking for friends, and so they're kind of unhappy. So getting rid of those, of course, send them off to Paris or something like that, mutate them away, and now they'll be happy. Okay. So by their nature, I think that they really need to be unsatisfied to be functional, and that's going to lead to stability changes. Now, there's some interesting sort of paradoxes that come out of all of this, and some of them are sort of accidental, but I want to address them because you still read literature where people say things that are completely ridiculous. So, thermophilic proteins that are from organisms that grow in very extreme temperatures, hot or cold, but specifically I'm thinking about hot. They have more stable proteins. They're proteins that work in boiling water temperatures because that's where those organisms live. Okay, C-vent things and whatnot. So clearly stable. We know about Taq polymerase, okay, and all those great thermostable polymerases that make PCR possible. Those weren't engineered by people; they were engineered by nature. So clearly, those things work, right? But if you put them in the laboratory and analyze them under kind of normal conditions, like you'd analyze any other enzyme, they typically are pretty bad catalysis. Okay, they're pretty bad. So there's really two reasons for that. So one reason that is often hypothesized is, well, they have to be bad in order to be stable. Okay? Kind of the reverse of the argument I just gave you. Baloney. Baloney. It turns out that basically, again, you have to go back to your evolutionary question. Why is anything the way it is? Well, it's that way because evolution requires it. So one thing is, obviously, if you then go up to the temperature that it normally operates at, okay, you find that it achieves the same rates as your typical enzyme that's operating at 37 degrees normal. So the rate, the flux through the enzyme is the same. It's just condition dependent. And again, we can get into reasons why cooling them down makes them less active. However, if you look at their rate accelerations, and what I mean by that is their actual catalytic ability. And how do you do that? You compare the catalyzed reaction to the uncatalyzed. What you find is that the thermophilic enzymes are less good catalysts. I don't mean K-cat over K, I mean K-cat over K-uncat. They're less good catalysts. Why? Because thermal energy is supplying a lot of the energy to get over the activation barrier continuum. Okay, so you don't need to be as good a catalyst because what life is selecting for is the flux through that enzyme, not its inherent catalysis. It needs to have a certain amount of metabolite or whatever converted at a certain rate to live, and that's all that's being selected for. The rest of it, okay, is basically, it's as good as it needs to be. And at that temperature, there's plenty of free energy from the environment to drive the reaction. The bigger problem is making sure it doesn't do things it's not supposed to do, damage metabolites. And so really the function of an enzyme there is to still act as a catalyst. It doesn't have to be as good, but it can then funnel reactions down particular pathways rather than letting them sit around and cook. Okay? Many metabolites are thermal sensitive. So I guess what I'm trying to say here is that, you can make a protein as stable as you want, okay, by evolution. You can make it as active as you want by evolution. Those are not necessarily related to each other. They're orthogonal, okay? But they can be related when you start doing mutations, okay? So the reason that you have a functional residue has to be destabilized is because it needs to be able to make interactions, all right? But I guarantee if you took those thermophilic enzymes and started mutating their functional residues, they would become more stable too, okay? The evolutionary pressures are what determine the properties of an enzyme, not some sort of abstract idea like this. Okay, so any questions on that? All right. So if you were to look at a profile of mutations in a protein, say you subjected every residue to alanine mutations, the alanine scan throughout the entire protein, you now have reasons to be able to pick out residues that do different things. Residues that cause big destabilizations are ones that are important stabilizing structure. The residues that you take to make the protein more stable are probably that way for functional reasons. They're probably the functional important. Okay. So let's talk about salt bridges. Another important and something that's in every single structure. So they're ubiquitous, okay, hydrogen bond and iron pairs in every single protein of any reasonable size. And if you find a protein that doesn't have one, come and tell me, and I'll talk about it. Okay. Salt bridges, so let's be clear. These are things that are observed in crystal structures. Hydrogen bonded ion pairs. Okay, so that's what defines the sense of salt bridges. But that's not really true because it turns out that many of these are not actually important for stability, the ones that you see in crystal structures. Okay, and where these guys are is they're usually up on the surface. You have two residues that have opposite charges, and they're making a hydrogen bond. They're ordered in the crystal. Reality is you go to NMR and you determine their pKs, and their pKs aren't shifting. That means that they are not interacting in solution in a meaningful way. If they were, there would be a pK shift. So just because you're an ion pair, the crystal structure does not mean you're a true salt bridge. You have to have a pK shift that indicates the favorable interaction. Okay? The ones that are energetically important, the ones with pK shifts, have very distinctive locations. They are partially or fully buried. Okay? Why? Because they have to be in an environment where water can't do the work of the other residue. They usually also have more than one set of interactions. They're rarely isolated between just each other. Okay, I pretty much said that they have to be stabilized, and they have to have pK shifts that indicate that. And so both residues are going to have pKs shifted towards their ionization. Okay, they're going to become easier to ionize in the folded protein than when they're not. The result of mutagenizing these guys is that you get very non-additive mutations, and this is a general property of any residue that's interacting, and I'll talk more about that in a little bit. Okay, so let's talk about salt bridges. All right. So this is an example of a salt bridge. I call it the famous salt bridge because it's the first one that's thermodynamically characterized. That's why it should have been in science, but it was in biochem. And what this salt bridge consists of, for the most part, is an aspartate at position 70 and a histidine at position 31. And this is T4 lysozyme. This is looking into the active site cleft. I've been showing you views into this part of the structure. This is the N-terminal domain. This is where that salt bridge lives, okay, right at the base of the active site. Mutations don't really affect activity. Okay, so it's definitely not involved in activity. It's involved in something structural. Okay, what are the facts? The facts are the pK of these residues are 9.05, and this aspartate residue has such a low pK, it really can't be measured. Okay, in other words, you can't get the protein to a low enough pH where you can fully protonate it. So it's less than 0.5. Okay? If you calculate then, so the pK shifts are then these, okay? And then if you calculate the delta G of ionization, okay, you get minus 3 kcals per mole for histidine and a bit more for the aspartate. Now, right away, you may say, okay, that's cool. But that bothered me when I first learned about it because if they're interacting in a mutual fashion, they should have the same energy of interaction, and therefore the pK shift should be the same energetically. But it's not really fair to do that because you have to ask yourself, is everything else the same under the conditions, for the rest of the protein, under the conditions where I'm measuring the pKa? You remember, where do I see the pKa? I see it right around the pK. That's where I have to get the data. So this pK was measured around pH 9, and this one was measured at very, very low pHs. They're not the same condition. So the fact that those are different numbers shouldn't be surprising because you're really talking about two different proteins here. You're talking about one which is at pH 1 and one that's at pH 9. Those are really different conditions. So it doesn't surprise me that they're not the same. If we could measure pKs without shifting the pH, which is kind of hard to do, then we should be able to see that they would be the same. But they should be energetically, symmetrically interacting. For the most part, you guess that they are. Okay, so what is the overall result of this? Okay, because this is really the first paper where somebody showed this, is that the electrostatic contribution alone, okay, of this residue is 3 to 5 kcals per mole for T4 lysozyme. The overall stabilization of T4 lysozyme at its most stable pH is 15.5 kcals per mole. So, in other words, this is about a third to a fifth of the total stabilization of the protein. Furthermore, it has 5 key salt bridges that are known, the pK shifts are known, and you can calculate their contributions to free energy changes, and they basically add up to be about the total stabilization of the protein. That should bother you. Because we know there's a whole heck of a lot of other stuff that we've already talked about, all right, that's adding up to more than 15 kcals per mole. So this is the other part that's a little bit hard to understand. Like, well, how can I have these individual interactions? They sum up to be way more than the actual voltage energy. And so what I'm going to posit to you is that if you mutate one salt bridge, the other salt bridges don't stay the same. They actually change. Their pKs are also different. Okay? And that's because, again, you have all these interactions that point to one singular structure. Anything you do to that is going to perturb all those other interactions potentially. Okay? And that gets into this business of non-additivity. Salt bridges, for a long time people studied acid denaturation. So I don't know if you know this, if you add acid to proteins, they unfold. Anyone ever here do a TCA precipitation of proteins in any of your lab work? You add trichloroacetic acid and your protein turns white and plops out, and then you can spin it down and then load it onto a gel. So people use acid to precipitate proteins all the time. Small peptides don't typically precipitate in acid, though. The question is, what's going on? Well, I can tell you, you're not chemically damaging it. All right, so that's not the issue. The issue is that you're protonating the salt bridges, now the protein's unstable enough and it falls apart. So this is really the mechanism for acid denaturation of proteins, or basic denaturation of proteins, same problem. Okay. We also know that protein stability is pH dependent, and it turns out the salt bridges are a good reason, or a good part of the reason for that. Let's look at some evidence. So this is not a particularly great plot quantitatively, but it's good enough. This is the temperature of melting okay, for different T4 lysozyme mutants, different T4 lysozyme at different pHs, looking at the wild type in a mutant. So the wild type protein starts with a low melting temperature. That melting temperature peaks around pH 5.5, and then it gradually decreases. These are 3 different mutant melts, okay, at different pHs. D70N, break the salt bridge that way. H31N, break the salt bridge that way, or combine them together. Now, right away, the first thing you notice is that all these guys look the same, which is kind of interesting. And the second of all is they have definitely a distinctly different pH dependence. All right? And in fact, if you subtract these two, what you get is you get a titration curve that looks like a salt bridge titration. Okay. So, in other words, this difference is due to this difference in pH dependence is due to the salt bridge. In other words, salt bridges are determining the pH dependence of this guy. Okay, let's look at thermodynamic cycles again, sort of. So what's going on with the pKs and delta-delta Gs? So the starting point is that the aspartate has a pK of about about 0.5, and the pK of the histidine is 9.1. What happens if I mutate either of these guys? So if I mutate the histidine, if I mutate the aspartate to asparagine, the histidine now has a normal pKa. So that means all of its electrostatic interactions are with that residue. If I mutate the histidine, the aspartate pK becomes normal. Both of these correspond to about a 4 kcal per mole stability change. Okay? However, if I combine the mutations together, the stability of the doubly mutated protein is the same, okay, as any of these others. In other words, there's been no net change for adding the second mutation. That's called non-additivity. Because typically speaking, we expect from, kind of to a first approximation, if I mutate a protein in 2 different places, that I'm going to get some of the stability changes. That's called additivity. So it turns out that if I have a mild mutation, which are well separated in the 3-dimensional structure, where they really can't interact, this is in fact true, that the summation of all the individual single mutants gives you the free energy change for combining all those together in one protein. What this tells you is that those sites are not interacting. Okay? They have not been. On the other hand, you might have a situation where they're not this way. And that's because mutations are occurring at 2 sites that are interacting, or 2 or more sites that are interacting with each other. And the reason simply that this is the case is that you can't, you're talking about a pairwise interaction with these guys, and mutating either one of the pairs can cause a loss of that interaction. So once you lose the interaction once, you can't lose it again. It's already gone. So this mutant is a nice, extremely clean case where the second mutation has no effect, okay, because you've lost all the free energy change from the first mutation. Formally speaking, we can write this like this. We ask, what's the nature of the interaction? If we compare what happens with the stability changes from single mutations versus multiple mutations, okay, if I said they're equal, then they're not interacting. But what happens if you sum up all the free energy changes, and they give you a more positive number than the actual mutant that's got all the changes incorporated into it all at once? What does that mean? Well, it means that, in other words, the multiple mutant is more stable than expected, okay, from the sum of the individuals. This means that you have a favorable interaction. Okay, and again, you change this, you lose a lot of free energy. That's a big unfavorable change in free energy. It's positive delta T. If I do that to either residue, I get big changes added together, I get twice as much, more or less. But now I go back and I add a second mutation to those individual single mutations. I don't lose any change in free energy. Why? Because I've lost the interaction energy already. Okay, you only lose it once. So that's true. Now, there are also cases where the interactions are unfavorable. You have a residue that is strained. Okay, well, so now I'm getting away from salt bridges. This is also true for other types of mutations. And by the way, what I just told you is also true for residues that are packed together in a hydrophobic form. They're making van der Waals contact with each other. You remove one, you create a cavity, you lose van der Waals interactions. Take a wild type protein, make the other change, you lose the same. You make multiple mutants, you definitely get a less stable protein than you started with, but the stability change is not as extreme as you would expect it by summing over them, because the interaction energy that was between those got lost in the first mutation. So that's the next sense. Again, you can imagine cases where 2 residues are acting in an unfavorable way. It's not typical in most proteins, except in catalytic sites. So I'll take a synthetic situation. Right? Make an overpacked mutation where I have 2 residues, they're banging into each other. And now I remove one, I'm going to get stabilization. Remove the other, I'm going to get stabilization. I remove both, I'm going to get stabilization, maybe, okay, or get a stability change. But it's not going to be as favorable as I thought, because again, once I remove that bad interaction, I can't remove it again. I'll remove it once. Okay, so that additivity pattern will be different. Basically, I'll get a more negative change from summing up the single mutations than I would by the multiples together. Another place you might expect this is in an active site where there's, say, two charged residues next to each other. The same charge, like in spartoproteases, there are two spartates, they're right next to each other. And they definitely influence their PKs quite a bit. You remove one, you get stabilization. Remove the other, you get stabilization. Remove both, you get stabilization. But that stabilization isn't the sum of the stabilizations of the individual residues. It's less than that. Because again, you've lost the interaction. The first mutation, you don't lose it again. Okay. All right. So that's kind of the summation. So in other words, if I give you, again, some mutational profiles, I say, we mutate these residues alone and together, these are the results. You should be able to tell me whether these are interacting favorably or unfavorably. Okay, so to summarize salt bridges, and then we'll let you go. Basically, energetically significant salt bridges are almost always found in proteins, and they're almost always found in the partially buried or buried positions. They're usually larger network, which I'll show you next time. The PKs are shifted towards ionization because they're more favorable environments than in water. And then, these are important residues. Mutating them costs you a lot of free energy. So one of the questions I'm going to leave you with is, are they always stabilizing? You can try reading a paper which I put up by Bob Sauer, where he claims that they're not, and talk about it to me later. All right. Have a good weekend, you folks, and we'll see you on Monday. Wednesday. Have a great long weekend. Thanks.